Okay, at the end of the last instructional video, we had talked about the electromagnetic spectrum, and I had said all of the radiation, and we often refer to it as light, all of it travels in a vacuum at a speed of 2.9979 times 10 to the 8th meters per second. And this value is known as the speed limit of the universe. Nothing, absolutely nothing, can travel faster than electromagnetic radiation or light in a vacuum. Anything that people always say, but what if it did? But it can't, because in order to travel at this speed, matter has to be turned into electromagnetic radiation. Anything that wants to travel at this speed has to be turned into one of these forms of energy on the spectrum, and then it travels at this speed. It can't travel faster than itself. So this is the speed limit of the universe. Because it's a special speed, we give it a c. And so that means our equation V equals F lambda, we often write it when we're talking about light, we write it as C equals F lambda. It's the same equation. It's just with a C instead of a V. Okay, so I just wanted to come back to clarify that. All right. So now we're going to look at a few of the properties that we talked about in general with waves that I said I would come back to in light. And the first one is reflection. And if you're following in the notes that I posted for you, there's some pictures there. Okay, so we know from earlier when we talked about reflection in general that the reflection is when a wave hits a surface and bounces off. So in this case, it's when light hits a surface. So here's a light ray coming in, and we tend to draw the ray. It's really a ray that's parallel to the wave fronts. But like it just gets messy and takes too long to draw all the wave fronts coming in. So we draw the ray that shows the direction that the wave fronts are going. Okay, so, and we call it the incident ray. The incoming ray is known as the incident ray. And it's going to strike a surface. This line that I just drew, which is perpendicular to this is the surface. Perpendicular to the surface is called the normal, right? Back to when we did forces and we called the force that was perpendicular to the surfaces in contact the normal. So this angle between the incident ray and the normal is called the angle of incidence. And our law of reflection that we talked about earlier in this unit says that the angle of incidence will be equal to the angle of reflection. So this is my reflected ray. And this angle here is my angle of reflection. Okay, so my law of reflection, law, always true. My law of reflection then is very simple. It simply says theta I will always equal theta R. The angle of incidence will always be equal to the angle of reflection. That is true no matter what the surface looks like. So if the surface is nice and flat and smooth and a whole bunch of parallel light rays are coming in, then they're all going to go out parallel as well. Okay? But if the surface is all bumpy and stuff, the parallel light rays coming in won't end up going out parallel. They'll still obey the law of reflection. It's just now they're all hitting the surface at a different spot, right? The normal here is like this, so this guy's going to go off this way. The normal here would be here, so this fellow's going to go off this way. And the normal here will be here, so this guy's going to go off this way. They're definitely not going to be parallel. Okay? In this case, where they're hitting the nice smooth surface, this could be like a mirror or something. And so the image you would see if you put your eye here would be a nice clear image. This is called regular reflection. But if the surface is all bumpy, and this could be like the lab bench in our lab, right? You can see the outline of the image, but you're not gonna like cut your hair in that. This is called diffuse reflection. So you can still see the image, it's just not clear. Still obeys the law of reflection. It's just that because the surface isn't smooth. It's like if you're looking at yourself in the water and then a ripple forms in the water and the image gets blurry, right? So diffuse reflection is going to result in a blurry image. Okay, so that's reflection. Now I'd like to talk for a few minutes about the speed of light. So we know the speed of light in a vacuum is the speed limit of the universe. Nothing travels faster. But light enters other media, it's going to slow down. And how much it slows down by depends on the density of the medium. The more dense the medium, the more it slows. And so if we were to measure the speed of light in another medium and do a comparison between the speed of light in a vacuum and the speed of light in another medium, the number that we get in that ratio will tell us about the density of the medium. The closer this n is to 1, it means the closer the density of the medium is to a vacuum. So if the medium that we're looking at is air would be fairly close to density in a vacuum, and n would be pretty close to 1. If the medium is water, water's definitely more dense than a vacuum, so V is going to be smaller, which means N's going to be bigger than 1. If it's something really dense, like, I don't know, diamond or something, then V is going to be even slower because it's more dense, so N's going to be even bigger. Okay? So this N is called the Index of Refraction. Refraction, because remember refraction was the bending of a wave as it goes from one medium to another. So if the wave is going from this medium to a vacuum or vice versa, it's going to bend. So it's called the index of refraction. And how much it's going to bend is going to depend on how dense this second medium is. In other words, it's going to depend on how big this N is. So it's called the index of refraction. It's not going to have any units because this would be meters per second over meters per second. In a way, you could think of it like the coefficient of friction. Right? The coefficient of friction told us about the roughness or the smoothness of the surface. Didn't have any units because it was, when we found it, right, FFR is equal to mu Fn, it was the ratio of Fn to friction. So here, no units because it's the ratio of speed of light in a vacuum to just regular speed. Just like friction, it ranged from a small value to a larger value. The bigger the coefficient of friction, the rougher the surface. The bigger the index of refraction, the more dense the material. Okay? So that's the index of refraction. This is the speed of light in a vacuum. Speed in vacuum. And this is the speed in the second medium. We'll just say in another medium. Okay? And so the index tells us about the density of the medium. The more dense the medium, the bigger the N. N can never be less than 1. Because V can never be bigger than C. So N is always going to be bigger than 1. Now there's a table in your book that has some different indices, plural of indexes, indices of refraction. It's on page 379. So you might need it when you're doing some questions, okay? So I think somewhere in your notes I ask you to calculate the speed of light in water and in diamond. So maybe pause the video for a second. It's going to pause itself in a minute, or in 10 seconds, and find the speed of light. So N is equal to C over V is our equation. So rearrange it. V is equal